Today we have Arun, and Arun's going to talk about zero levels modules for quantum affine algebras. Thank you for coming.
Okay, so I seem not to be able to share the screen. Is that?
Do you need to make him co-host, Slava?
Just made, yes, sir.
Let
I
me
don't
try
seem to
again.
be able to do it. Maybe I don't know how.
Yes, I got it. Great. Can you see the?
Yeah.
Okay.
Yes.
Wonderful. All right. So, well, first, thank you to all of you organizing so well and for having me along. It's a pleasure to talk about this story because I think it's just a wonderful story. And so as Ben knows, I don't really feel like I know what a lattice model is, because every time I talk to him, I ask him, what's a lattice model? But I sort of live here in Baxter land where I'm supposed to know what a lattice model is. And so I've slowly been trying to figure out for myself. And part of that search has been this study of level 0 modules, which we started. So this is a joint paper with Finn, McGlade, and Yaping Young, which is mostly a survey of how I learned the story. And it has, if for no other reason, you can download it and put the pictures on your wall. There are lots of pretty pictures. So I hope that. All right, so the first thing I want to start with is this picture, which let's see if we can make it bigger. It's it's here. So let me start with this question, and that is, which modules have crystals? So I'm a big fan of crystals because they allow me to control the character theory of my representations. And so in this setting, I want to work with the affine Lie algebra. So G for me is the affine Lie algebra. And U is the corresponding quantum affine Lie algebra. And part of what we want to do, so I should put affine, quantum affine algebra, is that everything that we do for Lie algebras, we should do for the quantum versions. So I like to, and particularly for crystals, that's a useful thing. My notation is that for the finite domain, I follow Katz's notation, and I put the G circle on top, algebra, Lie algebra. And U circle, similarly, is the ordinary Drinfeld Jimbo quantum group. Okay, so the answer then to my question is that integral modules seem to be the ones that have crystals. And almost always, it seems that you can produce a Littleman path model or some other good model for a crystal if the module is integrable. Integrable means that the SL2 strings are finite. So if you restrict to any SL2, it decomposes as a sum of finite dimensional modules. Okay, so then the question is, well, how do you index the integrable modules? And the answer to that is that there is a nice indexing set for what are called extremal weight models. So L lambda for me will be the extremal weight module. And everything should somehow be related to the extremal weight module in your picture. That's the way I think about it. So the extremal weight modules are indexed by a set to call int for integrable. or so they're integrable modules. And H int decomposes into 3 parts: the positive part, the 0 part, which is the part that I'm most interested in, and the negative part. So the way that you set this up is you need the fundamental weights. So lambda 0, lambda 1 up to lambda n are the fundamental weights for the Lie algebra, the affine Lie algebra. And the finite Lie algebra has also fundamental weights. Which I call omega 1 up to omega n. And a very important thing is that these are related. So lambda I is equal to I plus lambda, and there can be a small constant there, which I think is usually called AI check or something. But most of the time, AI check is 1. So these are mostly 1. For in type A, they're all 1. And this is for so this is for I between 1 and n. Lambda 0 is just lambda 0. It's where it was before. So already you can see in this picture that we're drawing, let me draw another version of it here, is I've got a lambda 0 axis. And then I've got another axis here, which is my omega axis. Omega, well, in this case, I'm doing SL2 hat. So that's type A1. And then I just have one fundamental weight. So I have the omega 1 axis. So this is omega 1. This is 2 omega 1, and so on. And lambda 0 is here. Let me do that in black. And lambda 1 is here. So there are 2, lambda 0 and lambda 1, there are 2 weights for the affine Lie algebra, 2 fundamental weights for the affine Lie algebra, and then there's 1 fundamental weight for the finite Lie algebra. And then in the picture, I call this, let's see if I can decorate this here. So this line is level 0, and then this line is level 1, and so on. So if I put in 2 lambda 0, that would be level 2, and so on. So if lambda, I think of it as L lambda 0 plus some amount of omega 1 plus some amount of omega n, and this L, this coefficient of lambda 0, this is the level. All right. Okay, so well, I've got that written there on the left. So now I can define H plus Z. This is the non-negative span of the fundamental weights for the affine Lie algebra. So that's what we usually call dominant integral weights. And dominant integral weights should be sort of your favorite ones from Lie theory, because they index high models, irreducible highest weight models. The negative ones, so in finite type, the lowest weight modules and the highest weight irreducible modules are the same. You're just choosing to index by a different weight. But in affine case, they're different. So you get this positive, this red part of the picture is a whole bunch of highest weight modules. And then this blue part of the picture is a whole bunch of lowest weight modules, and they're just not the same. They're both collections of models are integrable models, but they're different models. And then there's these special ones, which are on level 0. And this is we use traditionally the positive span of the fundamental weights for the finite Lie algebra. So those are these green points here. But even though we're using the fundamental weights for the finite Lie algebra, these are modules for the affine Lie algebra. So there really are still U modules. So that's my picture of how they're labeled. Okay, so I want to build this for each one of these weights. So if lambda is in the integral, is an integral weight, there is a very special module called the extremal weight module. Which I call. And so if I'm in positive level, so if lambda is positive level, sorry, then L lambda is simple and highest weight. And so I should write that out just so it's clear. So highest weight. And it has a character formula. It's our favorite character formula is the Weil character formula. Weil-Katz character formula, let's say, because I'm working the affine case. So it's just like a Schur function, it's an affine Schur function. It's a alternating sum in the numerator, alternating sum in the denominator, and it's for the affine case. And similarly, for the negative level, I have an upside down. So again, L lambda is simple and lowest weight. And similarly, there's a Weil-Katz character formula. But if lambda is in level 0, then this module L lambda is not highest weight and not lowest weight. So it looks like, let's get a picture. There's, yeah. So it looks like this. It's a big tube, and it goes up. You can go up and up and up, higher and higher in the tube, and you can go down, 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 lower and lower in the tube. It just doesn't have a highest weight or lowest weight. So you can't like. But it has these weights along the sides, which are called extremal weights. All right. So I had it. Oh, it's right here. It's right here. So this is my presentation. This presentation is due to Kashiwara. And it works for not only for the affine case, but for any Kac-Moody algebra. You build a module. So the generators of this module are some things which here I've called U, W, lambda. W runs through the Weil group of your Kac-Moody algebra. So in our case, this is the affine Weil group. And I have one generator of my module. Where did it go? Where's my picture? Oh, here it is. Right. So I have one generator for each one of these black dots. So you can see there are 6 black dots on sort of each tier of this module. And those black dots, those are these generators. So there's an infinite number of these generators here. And they're indexed by an orbit of the affine Weil group. And so that's all of those guys. And then there's relations. So you can see here that this is a generator of my quantum group. The E, the C are generators of my quantum group. And then I mean, I could even give you those. If you hear the generators of the quantum group, the D's, the E's, the F's, and the C's, and then it has these wonderful relations, which I'm sure you all know and love, right? And have memorized. But so the point is that I have rules for how to move these vectors around, these black dots. And it's actually very simple, the way to think about it. So you should think about it as like this. So this is the vector that we would call UW lambda. And then I have these E operators. Let's put the E's like this in purple. No, these are the F's, sorry, that move like this. So these are the F operators. And if I get all the way to the other end, then the F sends me out to 0. So this is USIW lambda. And the E operators, they move me upward like this. And if I get out to the other end, that sends me out to 0. So that's all these relations say. E goes out to 0 if you're at this end of the string. So if you're at the positive end of the string, then EX by 0. If you're at the negative end of the string, then FX by 0. And E has to take you from one end to the other, and F has to take you from one end to the other. So that's how you parse these relations. And this is a presentation for the extremal module, and it works for any level. All right, so that's how that game goes. And then Kashiwara Drinfeld says, fortunately, because these relations are so yucky and messy, the quantum group has another presentation, fortunately, right? And so we can look at that presentation, and that presentation only has these relations. So this is the second presentation here, loop presentation. And the loop presentation has usually P's and X's. And so these, let me highlight them here. So these are the X's. They're generating my quantum group. And then I have these E's. And just in case you need the formula for the E's, well, the E's are defined by this exponential of the P's. And these P's are to have Heisenberg algebra. As you can see, these relations are even simpler, right? They're about 2 pages long if you check them. And Drinfeld thinks this is better, and I do too. And why is it better? Because now in this guy, generators of my module. So first of all, I should say this is for level 0, that I have this loop presentation. I only have to take one black dot. I only need one vector to generate my module if I use the loop presentation. And in the loop presentation, this kind of looks like a highest weight vector, highest weight like. It's not a highest weight vector because it's somewhere on the side of my tube, but it feels like a highest weight vector in the loop presentation. So this is, and then I have these guys. These are elements of a Heisenberg algebra, which you should think of as elementary symmetric functions. So in the loop presentation, there's a Heisenberg sitting inside there. See these P's in the loop presentation act like a Heisenberg because of this red relation. And so what I do is I take the elementary symmetric functions here, and when they act on my generator, they kill it, provided I've got a large enough index. And the negative e, it kills it, provided I've got a large enough index. So somehow it's really wonderfully built to write down this loop presentation. Okay, great. So the next thing I want to do here is talk about finite dimensional modules. So finite dimensional models, two things happen, first of all. These are integrable. Well, no, actually, let me take that out because it depends on the way that you think about it. But they are always levels. So according to my philosophy, I should somehow relate the finite dimensional models to the extremal weight models, to the L lambdas. But the L lambda is very infinite dimensional. It's got this huge long tube. So I need to somehow make it finite dimensional. And the way that you do that is with a Drinfeld polynomial. So a Drinfeld polynomial is an element of the polynomial span. So I take polynomials in U of the fundamental weights for the finite Lie algebra, so the omegas. So that means that if I'm looking at these guys, I take a polynomial, it's really n polynomials. I have A1 of U, omega 1, all the way up to AN of U, omega n. But just like for the finite Lie algebra, I think of integer linear combinations of fundamental weights. Now I think of polynomial linear combinations of fundamental weights. And so let's let lambda, so given such a polynomial, let's let lambda be m1 omega 1 up to mn omega n with mi equal to the degree of AI. All right, so given a Drinfeld polynomial, I can very easily get an integer combination of the fundamental weights just by taking the degrees of all of them. Okay, now I can build the local vile module. So the local vile module is, so I'll call it M finite AU. Is L lambda with the extra relations that whenever this elementary symmetric function acts on the generating vector, it gives me, no, let me say it a different way. So if I take the generating function for all the elementary symmetric functions, so E plus I of U is the sum, well, 1 plus x positive I U to the S. Too many U's, but that's what happened. Okay, then this should be just AI of U lambda. Okay, so I'm forcing each elementary symmetric function to act by a constant. Right? So it's just killing all of my, it's like specializing your polynomial, your elementary symmetric function, you're specialized it to a number, which is the So how do I say this better? If you factor this into roots, then the coefficients of this polynomial are the elementary symmetric functions in its roots. So I'm somehow taking all of the variables in this Heisenberg algebra and specializing them to values. All right, so it has the effect of completely shrinking this module down to a finite dimensional module. All right, so now we, yeah?
For the local vial module, are you working over the full affine Kac-Moody-Lie algebra or the derived subalgebra?
The derived, I mean, you should work over the derived subalgebra unless you add some extra data, yeah. It's easier just to throw away the D, otherwise you have to say some fancy words, yeah. Let's work over the derived subalgebra, yeah. Okay, good, so now the theorem is, let me give myself a little more room here. So that I have a bijection between simple finite dimensional U modules and Drinfeld polynomials. Which we'll call AU. And this bijection just sends AU to what we might call L finite of AU, which is by definition M finite of AU mod a maximal proper submodule. So the finite, these local vial modules, they act like Varma modules for the finite. Head up at the top, and that head is the irreducible. So the M finite is not irreducible, but the L finite is irreducible. And I can build all of the irreducible finite dimensionals as quotients of the M finites of the. All right, so that's connects the extremal weight module. So the point that I want to make is that this extremal weight module is used to produce this finite dimensional thing, which is used to produce this simple thing. So everything comes from the extremal weight modules. And the way that I picture it in my head actually is the extremal weight module is this big, huge tube that goes up infinitely. And when I do this game of making the elementary symmetric functions act by constants, what that does is it takes the tube and it wraps it around into a torus. So my tube now looks like this, where my tiers are somehow around like this. These are these 6 dots that you see in these tiers. And then of course the tiers are connected by edges that wrap this module around. So it becomes very periodic. And that's why it's finite dimensional now, because you can only go so far around the torus. So that's gives you a picture of how these work.
Can you say what the dimension is of these finite dimensional U modules?
Yes, sort of, yes. Let me do that next. There was another question before?
I was just going to ask Arun how I should have guessed that, because you know the tube was presented with the old presentation and this is in the superior Drinfeld presentation, right? Why should it be obvious that the tube gets wrapped into a torus with this condition?
It's only, for me, it's not obvious at all in the Kac-Moody presentation. But when I go to the loop presentation, the Heisenberg generators just more or less act by pushing you up and down the tube. And then it becomes almost obvious, because if I force of one of the generators to be equal to one of the other generators. It just wraps that tube around. Yeah. Okay, so now let's go to the characters of crystals and characters. Question about the dimension. So I find this really completely amazing, this game. But so lambda in this case is level 0. So it's one of these points with no lambda 0 in it. So on that green place. And I'm going to let B lambda is the crystal of the large extremal weight module. All right, so the whole tube, I'm taking the whole tube. And then I'll let B finite lambda be the crystal of this M finite A mu. And that crystal actually does not depend on the polynomial, it depends only on the lambda. So the crystal loses the information of the constants in the polynomial, and so B finite. Okay, now I need two other numbers here. I need let me use K first. Let me write this first. S lambda is the set of tuples of partitions, kappa 1 up to kappa, let me write n, such that kappa I is a partition with length less than or equal to, less than, not less than or equal to, but less than mi. All right. And K will be a number of mi which are non-zero. Non-zero. Okay, so now let me tell you the structure of the crystal. So this is what I call periodicity. And this is an amazing theorem which is due Nakajima, and we could add many people have studied this. Braverman, some important geometric connection, semi-infinite flag variety. Nakajima was working with the quiver variety. Fourier, Littleman made some important steps in there. Naito, Sagaki made some important things. Actually, many people have studied this thing, but it really, Nakajima and there's another, maybe Beck, right? They really put the structure in that we're seeing here into this crystal. Okay, so the periodicity theorem says that the big tube module is made by taking the finite crystal, so that's a finite crystal, and repeating it a whole bunch of times. All right, so this is the core, if you like, and this is the repeats, the periodicity. All right, so and maybe we can get another picture here of what one of these actually looks like. So yeah, so this is a good example of what one of these crystals looks like. Is you can see that I have a core here of nine vertices. So there's 3 plus 3 in the middle plus 3 on the left. So there are 9 vertices, and those 9 vertices are repeated over and over and over. And that's what this theorem is telling us. So now the character of this part, this z to the k s lambda, this is the character of a Heisenberg, part of a Heisenberg, but let me write it down in Q form. So it's the product over I going from 1 to n of a factor which comes from this z part, q to the r mi. So remember that my lambda here is m1 omega 1 up to mn omega n. So this first factor is this infinite power series. It goes positive q's, q to the rmi, all for all positive r, and q to the r. So it's a infinite power series. Don't try to multiply very much, it gets very confusing, but I'm just trying to label the structure of this crystal. And then I have another factor here, which is the product k going from 1 to mi minus 1 of 1 over 1 minus q to the k. Too many k's. Let's change this to j. All right, great. So this part, you can already see here that this part is a generating function for one component of this S lambda, because S lambda was a tuple of partitions. And the generating function for partitions is 1 over 1 minus q to the j. That's this bit here. And this part is the generating function for one of these z's. It goes in infinite in both directions, just like the integers go positive and negative. Right. So, but what it's really coming from is that Heisenberg algebra inside the quantum affine algebra. And then the character of this finite part. So now this is the answer to the question about what its dimension is. It is E W naught lambda Q0, where E mu Q0 is the non-symmetric McDonald polynomial at t equal to 0. So I have actually been, you have to be quite careful here with your Q's and your T's. So I will remark here that I'm working with UT of G. That's my quantum affine algebra U, where the parameter is a T, and the Q is e to the delta, where delta is the imaginary root in this game. So the character on the left-hand side, we expect it to be a module for the quantum affine algebra. So its characters should be labeled by weights of the affine algebra plus a delta, which is somehow this tube part of the up and the down in the tube. And you want to keep track of that everywhere, and that's what this polynomial is doing for us. Example, in this example that we have the picture of, this McDonald polynomial really does have 9 terms. Well, at t equal to 0, this McDonald polynomial has 9 terms, and that is then repeated according to the periodicity that's given here. How does that feel so far?
I'm slightly confused here because I usually think of this 9-layer part as being the crystal for the irreducible, which would be a tensor product of Kilarov-Reshetikhin modules, and not for the local vial. And I don't see like any sort of trivial periodicity. Like I would think of my tube as just having like one layer rather than multiple.
So I didn't understand the last part, but you're telling me that generically this this M finite is irreducible. So yes, you often do see this guy as an irreducible, and I think that for this particular lambda, they might all the quotients might be irreducible. I don't. But yes, I agree that in this example, this is an irreducible model.
Okay.
I didn't understand what you were saying about the periodicity being.
Well,
just a
I think it's
period.
like on the next slide up on the right, where you drew the tube. No, on other side. Sorry.
This way?
No,
Oh.
the other set of slides.
This one?
No, the one that has crystals plus characters.
Oh, okay.
To me, it's on the right-hand side, but
Yeah.
if you scroll
Okay.
up, you have that torus.
Oh, okay. Yeah.
Yeah, and so you have those black rings, and I think of, you know, I at least from this perspective, I think there's only one black ring. Do you have an example where you have multiples of those? Because I don't quite see that from this, at least how I think of things. I'm just a little confused by that.
So there are examples where there are multiples, but in this theorem, I'm not really talking. This theorem is not really about the crystal of the finite of the simple module at all. This theorem is really about the crystal of the compact module. Maybe that helps. And so if I was to actually write down crystals for the simple modules, then I would have to divide this right-hand side up in funny ways. It splits up in funny ways, yeah. But here, everything is just Weyl modules. And the periodicity is really infinite, because I'm really looking at the crystal of the global Weyl module. I hope that helps.
Thank you.
Okay, great.
May I just to confirm, your variable q is well, one could just let it be a formal variable, but so you're making a choice that q is e to the square root of -1.
No, e is a formal. So when I write these characters, I'm writing. So how can I say this well? So if I just took hz to be the z span of lambda 0 and the fundamental weights and the delta, then I take the group algebra of this guy to be whatever span, the span of some formal symbols, e to the lambda for lambda in, let me call it mu in hz. So that's where my characters lie. And then I just make a convention that e to the delta, I call it q. Right? It's like your Schur functions depend upon a bunch of variables, and so it's not an actual number in this story.
I see. Thank you.
Sure. Okay, great. So what is it good for? Well, I don't really know, except that I feel like it must be really good. And this is, so I want to let C be the category of app-edge level 0 modules. And I want to let O be the category of so app-edge is a word that I use especially when I'm working with the students in the working seminar. App-edge stands for appropriate adjective, which means that I don't know exactly what category I should be taking, but I know that it should be probably not all level 0 modules, but it should have some appropriate conditions to make it really nice. And so I think part of the game is to figure out what app-edge, what the definition of app-edge is. But it stands for appropriate adjective. All right. Okay, so now let's let V be a finite dimensional module and generated by some vector, which I'll call, well, here I called it M nu. Let me call it that. So the affinization is you just take this module and you affinize it. So Z should be thought of as the loop parameter in my loop group, in my loop Lie algebra. So one favorite reference of mine for this is the book of Hong and Kang, page 233. Okay, so then you look at what is a vertex operator according to Frankel-Reshettichian. So now I'm going to follow, well, there are two wonderful references. One is Date Jimbo Miwa, 1993, and the other is for Frankel and Reshettichian. And that's in 1991. So they say do the following. They say, let's take mu and lambda to be an HZ plus. So maybe we can go back to this picture here. So I'm choosing 2 points in the red region. That's what it says. And I have, for those guys, I have an extremal weight module for each of those. What do I do is I transfer that by VF, which has to be level 0 because it started out as a finite dimensional module, so it's level 0. And then I look, what is a vertex operator? A vertex operator, they say, is a morphism. So the usual notation is like this. From L lambda into L mu tensor VF. So from my point of view, we're studying, when we study vertex operators, we're studying the action of C on O. Because the purple guys are highest weight modules in category O. And the blue guys are level 0 modules in category C. And somehow what this whole game seems to be about is that you take something from O, you tensor it with something from C, and you get something back that's in O, right? Or appropriately. So I took something in O, tensored it with something in C. When you take a module of level 10 and you tensor it by something of level 0, you get another module of level 10. So 10 plus 0 is 10. So this provides an action of the category C on the category O, which preserves level. And that seems to be what a vertex operator is. So somehow there's no possible way that I can study vertex operators without understanding this category C. Now, which part of it, they're multiplying by some very special modules from category C. And so that's why I don't quite know what app edge should be. All right. So then the next thing is that I can look at, oh, I'm getting close to the end of time. When do I have to stop, Slava?
Just depending where you are, but at 3 p.m. In Pacific time. So
Okay,
in 7
7,
minutes.
so 7 more minutes. Yeah. Okay. So I'll talk about Fock space then, and we'll leave it at that after that. So I find this beautiful paper of Kashiwara, Miwa, Peterson, and this is, so I want to make it, so Martina Lanini and I and Paul Sobaji, we have a paper about Fock space, which is really a different Fock space. So this is, so we talk about some abstract Fock space in that paper, and I want to stress that this Fock space is different from that Fock space. Although they're in type A, they probably do coincide, but in general, they don't coincide. All right. So the game is as follows. We want to look at wedge products in the category C. And this is really quite amazing that you can take this module VF and you can define a wedge product of it as the tensor product modulo some submodule. So I find that just completely amazing because even for quantum groups of type C, it's hard to make wedge products, for example. For quantum groups of type G2, I normally don't know how to make wedge products, but they have managed to do that. And then they build a Fock space. Well, they build many Fock spaces, but in this category C again, are semi-infinite versions of this. So this is semi-infinite wedge of VF. So this is really just taking n to infinity, but n is always positive, so as taking n to infinity. They also explain how to do this limit, which I will. So how do you build this ideal n? Well, it's like you think, sort of like you think it is. You should put some anti-commutation between the kth and the k plus first spot of your tensor space. So this is some anti-commutative relation. So that's what this n does for me. So this is sum over k here. And they explain how to get this n, how to make this anti-commutative part. So they take the highest weight vector, and this is because it's n now. And so this is my extremal weight generator. Extremal weight generator. And I use that like a highest weight vector because when I'm working with loop presentation, that sort of acts like a loop highest weight vector. And then I take its span and I include only some very special part of the Heisenbergs. So Z tensor Z moves both tubes. So I've got a tube tensor, a tube, B tensor V. and it moves both tubes up one. That's what Z tensor Z does. And Z inverse tensor Z inverse moves both tubes down one. And then Z tensor 1 plus 1 tensor Z takes your linear combination of up 1 and down, up 1 on one side and 1 up 1 on the other side. And this spans, you act on your extremal weight vector by those little shifts of the guy, and that produces the thing that you should quotient by to make your anti-commutative part. And they prove an amazing theorem which says that this is actually the kernel of r minus 1 times psi, where psi is the factor that removes denominators in this spectral R matrix. So maybe I should write R of Z here. So this is an R matrix minus 1. So I remove the initial part of the R matrix, the constant term of the R matrix, and then I remove the denominators, and then I look at the kernel of that. So R of Z. So this says you can produce Fock spaces that work in all types, for all groups, for all level 0, but you have to do it in level 0. That's what I find the most amazing. All right, I'll stop there then. My time is.
Yeah, let's thank Arun. Okay, let me stop recording.